Hi, and welcome to Mathematics with Tom. I am Tom, and today we're going to talk about three topics that are very closely interrelated. These are called independence, span, and basis. And this is covering chapter 3.3 in our book by Gilbert Strang. So I'd like to begin with just the definition, and then we're going to take a look at examples and see how this all comes together. So here we go. I'm going to say this. Our definition is this. A set of vectors. A set of vectors. We could call them V1, V2, and we can have all the way up to some V to Vm are linearly independent, when x1 v1 plus x2 v2 plus all the way out to our last xn vn equals 0 such that x1 is equal to x2, well that has to be equal to the x3, and that has to be equal to x4 all the way out to xn, and all of the x's are 0. That's what it means to be linearly independent. And also you'll regularly hear this not as independent, but you'll just hear it shortened down to, you say vectors are independent. So those are used interchangeably. Now, the next thing is the complement to that would be vectors are dependent. Vectors are dependent when not all xi, and to be correct, I should say this is I is in the set from 1 to 2 to whatever n we have, when not all xi are 0. Seems simple, and at first when you hear this it seems like it might be a bit confusing, but I'd like to come back down a little bit and let's see if we can boil this down to something that might be surprisingly familiar. And that is instead of writing from x1 all the way out to x1 v1 to xn vn, let's just look at a smaller example. How about that? A smaller example. A smaller example is, let's just look at from v1, v2 to v3, because we've been working with 3 by 3 matrices. 2 by 2, sometimes it's a little simple. 3 by 3 is enough that you start to see the pattern. And that's the general rule in math, is if you need to show a pattern, you want to show the first 3 examples, or 3 parts to the pattern. Well, let's take a look at this. So if I write out what I'd written above, I have some scalar x1 times the vector v1, plus I have the scalar x2 times the vector v2, plus I have the scalar x3 times the vector v3 is equal to 0. Now, be careful, when I say this 0, we're thinking contextually, and contextually, that 0 is the 0 vector, because what is this? This right here, this summation here on the left-hand side, this is just a linear combination. This is a linear combination. Well, wait a minute. Let's bring that idea up here, because we've seen this before. And you might say, wait a minute, I know I have, but it's not coming to me. Well, here's why. It's what it is, it's not why, but let's just show you what you're seeing. This is this is the matrix equation. So a linear combination, remember, forms the matrix equation. The matrix equation AX equals B. All right, well, the columns of A in this case are the V's, and notice it. So we'll write that. The V and the key part, well, I'm going to write that in a second. The key part here is this, is that key. The key part is that B in this case, the B vector is the 0 vector. So now let's write this matrix equation. Well, the columns form the columns of A, so I have V1, V2, V3 times the scalars x1, x2, x3. And what this definition is saying is that has to be 0, given that all the x's are 0. So really what this says is that V1, V2, V3 times the 0 vector, 0, 0, 0, does in fact give you the 0 vector. And that's the only way to get to the 0 vector, okay? So we're going to look at examples and see, to provide clarification for that. So let's go back down here. We're going to keep this in mind. I'm going to come down here and let's take a look at this. So let's try this. Let A be the matrix of 1, 1, 1, 2, 2, 3. Okay, and what we're going to do is the first thing we want to solve. We want to solve AX equals 0. Well, let's try that. So this means then that if I'm going to write these linear combinations, this means that x1 times the first column of 1, 1 plus some x2 times the second column, 1, 2, plus x3 times the third column, 2, 3, is equal to 0. Well, notice this. The third column is the sum of the first two columns. So what we could do, I could put a 1 maybe in this first scalar and a 1 in this second scalar, because we know that those two are going to add to this third one. And so if I just subtracted the third one, I would have 0. I would have 0. So right there, we've just found a solution. We just said, I'm going to call it S1. S1 is equal to 1, 1 minus 1. So what did we just do? The key point here is we found a non-zero vector that satisfies AX equals 0, so we can say, so the columns of A are dependent. Columns of A are dependent. Now, let's think about that. Normally, we haven't been taking our matrix equation and solving it by just looking at it and writing the linear combination. What have we been doing? We've been using our row reduction. We've been taking A to its reduced row echelon form, examining that, and picking up our solutions. Well, in a way, we already know the solution. Let's see how the algebra shows what we already know. So let's do that. So I'm going to write the augmented matrix here. And the augmented matrix would be 1. First column, we'll go by columns. 1, 1, 1, 2, 2, 3. And then remember, and I like the line here just for clarity, it has to equal the 0, 0 vector. And we said that oftentimes we don't write the right-hand side when it's simply zeros, but I wanted to today just provide clarity. Now, remember, our goal is we want to take the augmented matrix here of A, 0. We want to take this to the augmented matrix of R, 0. And remember that row operations will not change the zeros on the right-hand side. So let's try this. I'm going to take row 2, and I'm going to subtract row 1. And that's going to give me, I'll bring this down here, 1, 1, 2, 0, 0, 1. 3 minus 2 is, oh goodness, 2 minus 1 is 1. And then 3 minus 2 is 1. And 0 minus 0. Okay. Now, we're not quite done, but look at what we've done. It's so important. Let's use another color. I've got a pivot in the first column, first row. And I have a 0 down below. So that means that I come down this diagonal looking for my next row with a pivot, and here it is. My next pivot now is the 1. Well, it's in the bottom row, so to get to my reduced row echelon form, I need to zero out. I need to zero any elements or components above that. So let's do that. Let's do that. So I'll track this in yellow here. So we're going to take row 1 now, and we're going to subtract row 2. Wow. All right, so let's go back to our primary color here, white. So my first row now becomes 1. Then I have a 1 minus 1. 1 minus 1, 0. 2 minus 1, which is 1. 0 minus 0. And then my second row stays the same for 0, 1, 1, 0. Okay. There's a lot to see here, so let me see if I can help you see this. I think we can do this together. Notice a couple things. Notice no 0 row. No 0 row. What does that mean? It means we have a full column space. Full column space. So there's no restrictions. If we had a 0 row, we would have a restriction on what our vectors could get to into the column space. But in this case, we can get to anything in R2. So full column space and full column space in R2. Okay. Notice another thing. The rank R is 2. And notice that the rank is less than 3, which is the number of columns. So in this case, but our rank R is equal to M. So we have full row rank. Let's write that. Full row rank, not full column rank. Okay, I'm going to scroll up. I have a feeling that my picture is now right on top of my writing. So let's move our screen up. I'm going to take about half of this for a bit. Well, I'm going to need my piece. So let's do this. Let's bring, I want to bring all of this down so we can take a look at it together and not lose track. So I'm going to copy that. Paste it up in this corner here. Oops, not like that. Okay, that's a mess. Wonderful. And I think I need to undo both of those. There we go. All right, so let's move forward now. Sorry for that. let's see. Oh, what else do we have? Let's notice. Oh, yeah. Goodness, we do have more. Notice this, that our x3 right here, x3 is free. In other words, it's the independent variable, and so our pivot variables, x1 and x2, are dependent. So that creates a linear equation. It creates a linear equation that looks like this. It says that x1 is equal to minus x3, and it also says that x2 is, you know what, I did that really fast. Let me just go back a second. I did a bit of algebra in my head, and that's not fair. x1 plus x3 is 0. Well, we write our linear equation then in terms of our dependent variables, so I could say that x1 is equal to minus x3. And I can also do that again because x2 plus x3 is 0. So I can say then that x2 is equal to minus x3, like that, okay? Well, what do we get from that? Here's what we have. So we can say that our solution, x, is equal to x1, x2, x3. Well, let's write in what we know. This is x1 is minus x3. x2 is as well. And x3 is itself, it's free. So what does this give us? This gives us, I'm going to call it x3 times the vector minus 1, 1. And if you notice that this is equal to minus 1 times the s1 we initially found. Let me show you, I'm going to go up above. That is right here. I'll even put it in yellow. That's what we found, our non-zero S1. Okay, so what did we find? We just found that the null space, this is another thing that this says. This says the null space of A is more than the 0 vector. Okay, is more than the 0 vector. All right. Okay, I want to show you something else. Let's take a look at what we have. We're going to make a graph. Let's make a sketch. Here's my sketch. It's pretty simple. So let's see. I need to go out to a 1 and 2, and then maybe a little 1, 2, 3. So let's graph this. Let's go back. Remember what our original A is. Original A is the matrix 1, 1, 1, 2, 2, 3. So let's graph these. So this is going to be 1, 1. So I have, here's 1, 1. I have 1, 2. That's going to be this vector here. And I have the vector 2, 3. The vector 2, 3. Okay, here we go. Let's put all this together. What does this picture show us? It says that, notice that we can even go so far as just to show that, we already know this, that the first column, V1 plus V2, is in fact V3. But we also can see that, that any linear combination of these vectors is going to give us R2. So we say this, we say a couple things. The column space of A is R2, because there's no 0 rows. So what does this mean? This means This means that any b in the column space, which is all of R2. That's right. You could pick any vector and we could get there. This means that any b in the column space is a linear combination, of the columns of A. Okay, well, what does that mean? When this is the case, when we say that the vectors span this, we say that the vectors fill the space. We say it this way. We say that the columns of A span, should write that probably in yellow. That's a key word here. Notice that was what part of our title. The columns of A span R2. Another way of thinking of that is, another way of thinking of that is, i.e., the vectors can fill the space. And we say that by the linear combinations of the vectors. The vectors can fill the space. Okay, so let's pause there. Now, what do we want to do? I want to show you this. Look at this. I wish I had more space, all on one big screen. So here's what I think I'm going to do. Let's just do this. I'm going to take my picture here, copy that. Do this again. Paste it. Put it right there. Okay. Now, what else is this? Notice this. Notice column 3. I guess could have used V3. Column 3 is unnecessary. Necess is unnecessary because it is a linear combination of column 1 and column 2. Okay, now here's our next big piece here. When the number of vectors spans the space is the minimum number necessary then the columns form a basis for the space. And a space right now, this is our specific one. The columns form a basis for the space. For the space. And in our case, it's R2. All vectors with 2 components in them. And then, so wait a minute, what did we just say? Well, let's write this. Let me be specific, because now I just gave you another word that I probably should have put in yellow, and that is this one, the basis. And it's so important that let's define it. The basis for space is the set of vectors that meet 2 criteria. Okay, here they are. Number 1, they span the space. The vectors span the space. Number 2, the vectors are independent. The vectors are independent. Well, what have we just found? We've just found then that we could say that a basis for, in this case, for our column space of A, which is equal to the row, R, which is equal to R2, is the set of vectors that we can get from 1, 1 and 1, 2. It means all linear combinations of 1, 1 and 1, 2. And notice then that our basis, the number of vectors, this is even better, is the number of vectors in the basis is called dimension. I'll use a capital D, because it's another important vocabulary. So in this case, we would say that the dimension of A is 2. Okay. Now, let's see. Let's take a look. Let's try another example. All right, here we go. Okay. So I'm going to call this the matrix of A star. And that's because I'm going to modify my original A. And what I'm going to do is drop the third column. So I have 1, 1, 1, 2. That's it. That's going to be, and our A star. Well, the problem then works the same. Solve A star X equals 0. Well, we've already done that. And because, let me come up above. Let's come up above. If we look at A star, when we look at our work, A star, right there it is. Look at this. Nothing has changed. Here's the first 2 columns of A. That is hard to see, so let's use something that's not. So here's the first 2 columns of A. And then what did we do? Well, we went through our row reduction over here. The first 2 columns, they stay in the same place. So wait a minute. This reduces to just the identity matrix. Wait, we're almost done with this problem. So when I come back down here, what do I have? I have that A star 0 becomes 1, 0, 0, 1, 0, 0. But this is just the identity with with 0. That's just the identity with 0. So what do we have here? Well, we have our solution. This just says that x1 has to be 0 and that x2 has to be 0. So v1, or column 1, v1 and v2 are independent. Independent. Because are independent. And why? It's because we just solved that a star equals 0 only has the solution of 0, 0. Okay? So when that happens, then we have our independent columns. Now, what also does this mean? This just means then if you start with a star and you end with I, then that means that the columns of a star are independent columns, and those columns, so this says that the first column, and then this next pivot here says that the second column, those two columns form a basis for your space. Okay? Now, let's try another one. I'm going to call this one A prime. So A prime is the matrix of 1, 1, 0, 0. And we're going to do the same thing. Solve A prime x equals 0. Well, I want to solve this in both ways. I want to solve this both ways. First off, if I write this as a linear combination, I get x1 times 1, 1. Plus I have x2 times 0, 0. And somehow this has to equal 0, 0. Well, we know that x1 being 0 and x2 is 0. That would work. But is there another solution? Well, let's see. What if I said x1 is 0? What about x2? That's right. x2 can be any number, so it could be a 5. Well, wait a minute. That means I can still get to 0 without using the 0 vector. So what can I say? I can say the columns are dependent. And further, what that tells us is the 0 vector is not part of a basis, except for the basis if the null space is only the 0 vector. Okay? So the 0 vector is not part of a basis because any set of vectors that include the 0 vector is now a set of dependent vectors. That's the big takeaway there. And you can also see this if you were to solve the augmented matrix, because you would do a simple row reduction and you would end with 1, 0, 0, 0, 0, 0. Well, wait a minute. Now what do you have? This says we have a restriction because we have a row of zeros. So right off, the column space is not all of our 2. So since we just have a pivot, we just have our pivot here in this first position, it says that my independent vector is just this first vector. And when I look at it that way, what do I see? This just tells me that the column space of A prime is just the set of a set of linear combinations of 1, 1. So it's not a plane anymore. This is just a line. Just a line. Okay? And so we could say that the dimension of A prime is just 1. It just has 1 vector in it. Okay. I think I'm going to stop here, and in our next video we're going to take a look at a couple more basis vectors that may not be so obvious. Hope that helps. Thanks for watching.